Great. I gotta move my mic. There we go. Hopefully this stream is working. In the meantime, while people join in, I will verify that it's working. Oh, there's already a message in the chat. Nice. Yep. All right, it works. Sweet. Okay. So the deadline for the heap module is rapidly approaching. I think it's tomorrow with basically zero room for being able to push back modules. So hopefully everyone has had a chance to get a good start on the module, but either way, we will be going into it. Someone is interested in jumping straight to something like level 12. Someone else is saying 9 and 10, and I got a message before that someone was interested in like 9 or later. And then another person voting for 7. Okay, let's take, hopefully we can get a look at all of these. Yeah, Arizona especially, we don't have daylight savings. And apparently lots of votes for 11 as well. Okay, so votes all over the place. Let's start with the lowest number, so 7. But we will try to get through all of them. Okay. And we are on level 7. Okay, let's see what this challenge is asking us. Or giving us the ability to do in this case. I'd agree that daylight savings is a pain, but doing something different than everyone else isn't sane. Yeah, it basically means that Arizona is like truly the only place that actually has to deal with daylight savings because suddenly we change compared to everyone. But you know what? We're going to be trailblazers here in Arizona, and eventually the rest of the world will catch on. You know, I think the greatest thing would be if we just got rid of time zones altogether. Imagine if the sun set at like 9 a.m. Who cares? Doesn't matter. Everyone should just be on the same time. All right. Anyways, let's look at these heap challenges. This challenge allows you to perform various heap operations. Yep. Okay. All of these challenges have done this. Challenge 16 allocations. Good to know. Okay, so this is one of the challenges that has a secret stored, and it's stored in the BSS with pi disabled. The reason we know that is because it's this address that starts with a 4, which certainly implies that pi is disabled, and we just know that global data, it's going to be stored in the BSS. Well, not necessarily. It could be stored in the other, what's the other name? The BSS is basically the section where it all starts 0 initialized, and now the ELF doesn't have to store that. And there's also global data that's not in the BSS, and I don't know if there's a name for that. Just the data section? I'm not sure. Okay, either way. If you can leak out this secret, you can redeem it for the flag. And here are the operations that we are given. Malloc free, put, scanf, send flag, and quit. Okay. So how is this? Is this the same thing as the previous level, but just 16 bytes instead of 17 bytes, or 16 bytes instead of 8 bytes? Is it otherwise the same? I got the secret, but I don't understand why it's not authorized when I submit it when doing send flag. Just to verify, it is slightly different. So the thing to verify, I guess, about the secret is that you have definitely all 16 bytes, that you aren't reversing it as someone says in chat, and that depending on how you're getting at the secret, maybe you haven't inadvertently overwritten the secret. So if you manage to leak the secret out, maybe just try restarting the challenge and submitting it to get past that idea. And then you could also, if in case you reversed it, maybe try flipping the orders around. Yeah, inadvertently overwriting it would be is definitely a thing. Okay. Worked for 7.1, but not 7.0. And just to confirm, the secret you got is all lowercase alphabetic characters and 16 of them. So if you have something working for 7.1, that approach should be almost entirely identical to 7.0. I would wonder if you have things reversed. Okay, let me quickly go back to 7 again. Yeah, actually, mess around with it, and if you still can't figure it out either after this office hours or in a bit, message in the chat, and I can either go over it with you on Discord or maybe we'll have time to look at it also in this office hours. Okay, so just since we have so many levels, I'm going to go to the next one that someone's talking about. So someone else mentioned level 9. And I'm definitely going to have to think about how to go over this stuff without just giving the answers away. Because it's a little trickier on heap. Because some of this, a lot of these heap levels are like, understand the linked list, and then do a correct set of operations once you like truly understand it. Maybe there would be a little bit of creativity in there, but generally it's like understand the linked list. Okay, let's look at 9 real quick. Okay, heap operations, 16 allocations, there's a secret stored, and then this is an interesting quirk of this challenge. If you attempt to malloc an address near where the secret is stored, it will be discarded. Okay. So that means there's kind of like some sort of quasi-security mechanism here that if it detects that if it detects that malloc returns something that is probably somewhat near this address here, it's just going to presumably like null it out or something. But the thing to realize there with that, and maybe this is kind of like the crucial hint here, is that even though that malloc is being discarded, it still happens. The malloc still went through and effects on the T cache still happened. So there's things you can do with that in mind. Yeah, so hopefully that makes sense that even though it's throwing away the result of malloc, T cache is still being impacted. It's not reversing whatever happened to T cache. So really you got to think through what's happening when we do T-cache stuff. So for instance, if we start by doing malloc 032 for 0 allocation, 32 bytes, and then let's do malloc 132 and malloc 232 just to get a few things. And then let's get those all into T-cache. So free 0, free 1, free 2. Okay. So we have T-cache here. And basically, as I've said probably already many times throughout this office hours, and will continue to say throughout this office hours, T-cache is a linked list. We're just doing a bunch of linked list operations. So a crucial element of this linked list is this head pointer, right? In some sense, this head is kind of, in some ways, it's different than the rest of the linked list in that it is the start. So the head, the location of the head is, why is the key weird? What is happening right now? Why does this look weird? Hold on. You know, I've seen the heap do this and have this weird looking address before. Maybe we should just ignore it. Hold on. Yeah, let's just ignore it. All right, let's go back to where we were. It doesn't actually matter for what we're going to talk about. Free 0, free 1, free 2. Okay, and then I can see the secret value in Tcache from 9.0, but not 9.1. Oh, yeah, so I mean, you're saying you can use this right here as a way of leaking out the secret. But obviously this is just here to kind of effectively assist you in your debugging and understanding of what's going on. And using this isn't really meant to be part of the intended solution, right? Which is why we have these .1 variants that don't provide this for you. Okay, so anyways, what I was saying is we have Tcache. We have this head pointer that's kind of where the head pointer is located, as in the address in memory that this pointer is stored, is not one of our chunks in Tcache. It's kind of like somewhere else. So maybe that doesn't matter, but that's something to think about. But otherwise, all of these locations in memory, so for instance, the very first thing, and the head pointer tells us this, is that we have this 320 location that contains our very first chunk, that if we do a malloc of size 32 or somewhere around size 32, we are going to get this as our result back. And what's going to happen when we do that is that the linked list is going to update itself, because this, once we give this out, it's no longer going to be available to be given out. So let's see what this looks like. If we do now malloc 032, as I said, we get this 320 address. So 320 was located here. We get 320 back. Okay. And we had to do some other things, though. We didn't just return 320 to the person calling malloc. We also updated Tcache. So we replaced the head entry, because this is no longer, we can't give this out. So obviously it makes sense. We got to change it. And what we're going to change it to is the next pointer available in Tcache. So we go to this location in memory, which is being shown right here, where this is 16 bytes before, this is 8 bytes before, this is right at that location, and then this is 8 bytes after. We go right to this location, so this 320, this is what is right there, the first 8 bytes of that, and we just pull that out, and we make that be the head, because this is the next pointer. Hopefully everyone is already familiar with this kind of concept at this point in the heap modules. So we update this with that. Okay, so there's something subtle here, though, that's going on, right? That relates specific to this challenge. So it's telling us if you attempt to malloc an address near where the secret is stored, it will be discarded. We're not killing the program. We're not somehow unwinding the malloc. We're just discarding it. So for instance, if this value right here that we got back that was here, if this was close to the secret, say it started with like a 4, whatever the check is that's determining if it's close to the secret, allocation 0 would just suddenly become null. But Tcache would still look like this. Our security mechanism that we've implemented here is not impacting Tcache. So whatever is here is still going to be here. And maybe another way of illustrating that, so if I do, remember, is this allocation 1, this 2F0? 2F0, allocation 1. Okay, so if I scanf over this 2F0, so if I do scanf 0, and let's just do 2, 3, 4, 5, 6, 7, 8. Okay. What did I just... Oh, I did scanf 0. I meant to do scanf 1. Scanf 1. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we have these 8 A's here now. And this is about to be an issue. It's unfortunate. Do I need to switch to pwn tools? The issue is I need an actual allocated region of memory to show what I'm trying to show. Well, we can at least talk it through real quick. Okay, so if we do another malloc right now, right? So we've said that what's going to happen is that this is going to become the result of that malloc, and then this is going to become the head pointer. So if we do malloc 0, 32, and probably, I'm pretty sure we're going to crash right now. Maybe not. Interesting. Why did we not crash? No, of course we don't crash yet. Okay, so as I said, this is going to end up here, right? Everything we've, hopefully this makes sense. If this doesn't make sense to anyone right now, please let me know that this is the operations that's happening on the linked list. We return this to F0, we update the head pointer. Simple linked list stuff. Okay, but as I was saying, this data is still here. And probably the person that was talking about how they could solve 9.0 but not 9.1, this is probably what they were looking at. They were saying, okay, well, maybe my secret is here right now, or maybe somewhere else in Tcache. We're pulling that out. But what happens if we malloc, or if we free another thing? So if we do, let's say, free 0, or just free 0. Yeah, free 0. If we do free 0, something interesting just happened. And what just happened, right, is that we freed allocation 0, which was the 2F0 thing. We would have to scroll back to see that allocation 0 was 2F0. And when we freed it, we made this the new head pointer, right? Because whatever we free becomes the next head pointer. But the other thing, and this is the crucial thing for this level, is that we go to that location in memory, and the first 8 bytes of that location in memory, we write the old head to. So we just transferred data from the head, this first 8 bytes, to whatever we just freed to, this 8 bytes. In some sense, what we just did was a mem copy. We just moved memory, right? We copied it. And the way that we copied it, so let's see here. It's not clear because we already had 2F0 with these A's. Okay, hold on. Let's go through one more set of this just to show that this is a mem copy, that what we're doing right now. If we do malloc 032, malloc 132, malloc 232, malloc 332, free 0, free 1, free 2. Okay. And then if we do, if we want to overwrite this 320, 320 is allocation 2. 320, allocation 2, yep, 320. So if we do scanf2 and give it 8 A's, 4, 5, 6, 7, 8. Okay, so we just wrote our 8 A's to this 320 location. Hopefully that is clear, right? We just did scanf to it. 8 A's are now at 320. And what happens now if we do malloc 032? So our goal right now is to transfer these 8 A's at 320 to, let's say, this 350. We want to mem copy it. We're showing that this is a mem copy. So we have malloc 032, which gets our 8 A's up into the head. And then if we do a free 3, because allocation 3 is this 350, and this is where we're trying to copy those 8 A's to. If we free 3, we will see that now 350 contains 8 A's. We never scanf'd 8 A's to 350. We scanned it to a different allocation, and by abusing this linked list, we effectively got the equivalent of a mem copy. This is what I mean by like really deeply understanding this linked list structure and what's going on. That it becomes critical to pull out these patterns that, for instance, doing this sequence of operations, I can get a mem copy. And this strategy, I think, will be very useful for this level. Hopefully that makes sense. There was a question. Why was level 9 not PIE? Was it not? Oh, the person got 7. Awesome. Okay. Not PIE. Oh, I see. Yeah, it's not PIE, and you're wondering maybe it should be PIE. I think anywhere that we have a secret, I believe we have it be not PIE. Because we want you to know where the secret is, basically, is how the challenge is set up. And if we made it PIE, the location of the secret would be randomized. And that's not part of the challenge. Okay. All right, so that is what I'm going to show for level 9. The fact that you can do a mem copy, which is very, very useful. And obviously you have to think about maybe the next couple of steps in if we have a mem copy, well, how can I still get the secret out? But I'm going to tell you it's doable. But hopefully this mem copy idea is kind of the missing puzzle piece. Okay, so someone else is interested in discussing level 10. Okay. Level 10. Okay, so heap operations, 16 allocations. The local stack address of your allocations is at blah, blah, blah. Okay, so for some reason the challenge is the randomizing where the stack is. If we know this address right here, we know where everything on the stack is. The address of main is at here, so this just de-randomized PIE. So right now we know where everything in the binary is, everything in the stack is. We don't know where libc is, we don't know where the heap is, but we know these. So if you kind of think of it as 4 regions of memory, we have our stack, we have our heap, we have our binary, we have our libraries. We have 2 of the 4. We know where the stack is, we know where the binary is, we don't know where the heap is, we don't know where the libraries are. But this is what we know right now. And maybe we don't care about those other 2, just something to keep in mind of kind of while you're exploiting software, it's nice to know what you know. Okay, and then these are the operations that we have access to. We have malloc free, put, scanf, quit. Okay. Address of main. This doesn't say that there is a secret, and we don't see any function that's going to basically redeem a secret for a flag. So things that are jumping out right now is that if we know where the stack is. Okay, so here's what's going through my mind right now when I see this. We don't have anything that's going to be redeemable for the flag. So probably what we're going to need is we're going to need code execution. That's pretty much going to be the only other way to get the flag is if the program doesn't have any operations that lets us read out a file or specifically read out the flag, and we need to read out the flag, we need to get arbitrary code execution. And fortunately for doing arbitrary code execution, we've been messing around with these various primitives that kind of give us these arbitrary reads, arbitrary writes, and we know where the stack is, and the stack contains effectively function pointers, or more specifically, it contains saved instruction pointers. Those are kind of the 2 things you want to think about, kind of like a saved instruction pointer or a function pointer as kind of a means of beginning to hijack code execution. And we know where everything in the binary is, which means we know where a bunch of gadgets are or functions or whatever. So we know where code is, we know where a function pointer that can be overwritten to give us code execution is. So that's kind of what I would be thinking about right now. And one thing, I guess, to check, since it wasn't very verbose, but it's probably a good idea to take a look at what our binary has access to. Like what does our binary contain? If we know where all this code is and maybe we want to start doing ROP or something, probably not since this is a baby heap and not toddler 2, but we want to see what kind of code we have available. Oops. Okay, so if we just start scrolling through this real quick, don't care about this. Looking for dot text. We should probably just jump to dot text. Dot text. Okay, we have our start. We have random stuff that appears in every binary, more random stuff that appears in every binary. Get heap location. Oh, this is part of the teaching challenge that it needs to find the heap basically. Flag string, this is more heap stuff, more heap stuff, more heap stuff for debugging. Print tcache. Win, this is what I was trying to find. And obviously I knew that this was going to be here, but this is kind of how you would think about looking for this. So we have a win function that pretty much sums up this, this train of thought that we are trying to do arbitrary code execution. And arbitrary code execution to execute that win function. So if we run this, basically we know how to get an allocation pointing wherever we want it to be pointing from previous levels. And then we have the ability to scanf to that, which means we have the ability to start basically doing an arbitrary write. The only thing that would be missing here is where is a saved instruction pointer. And we could use GDB to determine that. So if we do GDB challenge baby heap level 10, and do I want this? I don't really want this. Hold on. Okay. GDB. And if we run the challenge and we, let's say, pause real quick by hitting just Control-C, which is going to kind of stop us in this read function, because that's what we're blocked on. And then we're curious about basically the distance between this and a saved instruction pointer. So if we do BT for backtrace, trying to keep in mind that my camera is blocking stuff, so I'm trying to format stuff correctly. But if we look at a backtrace of where we currently are, so we're in this read function, we can go all the way back up to main, and we see this. So if we do up to get to that stack frames context, which GDB lets us do, so now we're in the context of main, which means that we can print, for instance, our RBP, which is going to be main's RBP. And then if we do RBP plus 8, that is going to be where main saved instruction pointer is. And if we do, just to kind of show that, RBP plus 8, this is main saved instruction pointer, and hopefully it looks slightly familiar that this is like a libc looking address. In fact, if we wanted to verify that, we could do this, and we'll see, yeah, this is somewhere in libc start main, which is the function from libc that called us. Okay, so now we know that for this run of the program, the saved instruction pointer is here, and we're getting this leak that is over here. So if we just kind of, well, let's copy it. Let's switch here. Let's open IPython. And if we take this address that we've calculated in GDB, and we take this address that we are given, compute the difference. Now, whenever we run the program, the difference between the address that we're given, this, and this is 280, which means we always know where the saved instruction pointer is. No matter what, if we get this leaked to us, add 280. And for purposes of easily seeing it, we convert to hex. This is how we know where the saved instruction pointer is. And now if we kind of use the primitives that we've learned through previous baby heap levels, of being able to do these arbitrary writes, hopefully it's clear that we could kind of do an arbitrary write to that location and get arbitrary code execution. Are there any questions on that? This is kind of combining concepts learned in the previous levels as well as the idea of doing code execution. Oh, you're right. I didn't, I guess, mention that as well. The address of main is leaked as well. So if we do GDB the challenge again. So as I said, it's important at the very beginning to realize what we have access to, and kind of throughout as you build up your primitives and exploitation to realize what you know. Something we know is where the entire binary is, because we know where main is. So if we run, and in this case it's telling us main is here, which we can confirm with GDB that that is in fact where main is, and we know where win is, for instance. And if we do this minus that, similarly, we know where win is. Hopefully that makes sense. So no, you do not have to brute force the exact win address. Any more questions on this level? Okay. So that was 10. And then I think a lot of people were asking about 11. Yeah. Multiple comments asking about 11. Okay. Level 11 then. Let's see what the challenge does. Okay. Welcome to blah, 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 heap, blah, 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 16 allocations. Okay, so what are our functions? We've got malloc and free, as always. We've got scanf and quit, pretty standard. And I think echo, this is the first time you will have had echo. So if we want to demo this out, obviously we could open this in IDA to really understand it, but let's just test it. If we malloc 032, and then maybe we scanf 4, 5, 6, 7, 8, and then 1, 2, 3, 4, 5, 6, 7, 8. It's just, oh, that was not correct. What did that just interpret that as? What interprets that as 0? That's funny. All right, let's do that again, just to be safe. Malloc 032. What is this? We're going to call it sketchy. All right. Malloc 032, and we'll do a scanf on allocation 0. That is not what we wanted to paste. 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, and so instead of having puts, we have this thing called echo, which is probably going to be similar, but for some reason we have echo instead of puts. But let's see what echo does. If it specifies an index, so index 0, and it lets us choose an offset, which is interesting and definitely different than puts. Let's just do offset 0, and we'll see that it gives us this. Interesting. So it definitely gives us this extra ability to do offsets from there. The thing I would wonder though is exactly how this is implemented. So for instance, a quick way to see how it's implemented, and it's only quick because I know how it's implemented, but we'll use strace here real quick. And we'll do malloc 032, scanf 0, 1, 2, 3, 4, 5, 6, 7, 8, good enough. And then if we do echo 0, 0, we will see a very interesting thing happens, which is this clone syscall. And let me move that away from my camera. We see this clone syscall, and I guess I didn't follow the PID, but it's forking. So let's actually take a look at this in IDA. CD projects, ETF, pwn.college. We're looking at baby heap level 11. Okay. So I think this is going to be the quickest way to understand what's going on is just looking at it in IDA. Let's see what echo is doing. So this is the region responsible for echo. So we get our index, we get our offset, and then we call a function called echo. Okay. I guess what was being passed to it? E10. So this is our offset. Pointer V8. Okay, so this is allocations, index. Okay, so it's passing our allocation and an offset to this function called echo. And this is stack canary. So we have this V4 thing, which it's copying data to. Okay. And then we do a malloc. And then we're setting up some sort of argv thing, which makes sense because we're forking an execv-ing. So argv0 is bin echo. So we're directly calling the bin echo program. And then argv1 is this. So this like data string, data stir. Gonna ignore this crazy decompilation, just go with it. And then A1 was our allocation, we said. Allocation. And A2 is our offset, we said. We got 2 spammers in 1 office hours? It's crazy. Ban. Nice. Okay. So we're taking our allocation plus our offset as argv2. Okay, so we're passing bin echo. The first thing is just this data colon space, which is argv1. Then we're passing our allocation as argv2. And if we think back to how execve works, these argvs are null terminated. So eventually it's going to hit a null byte, and that's going to determine where we're going to stop echoing. So we definitely can't echo past the null byte in the same way that we can't puts past a null byte. And then we end our argv. Okay, and then we fork And this is like, hopefully you've seen this pattern enough times. If not, it's important to understand the fork exec VE wait pattern. Basically, we fork, we have our child, and the child we do an exec VE, and the parent we wait for the child to die. Very simple. Okay. And that is how we're calling bin echo with these parameters. Basically, it's just allowing us to echo stuff, but there must be a reason that this challenge has implemented it in this way, because you could imagine, if we want to get a little meta game that you could in theory just have like a puts with an offset, but for some reason it's not doing that. Okay, so the thing that stands out to me the most is that since we're operating in these heap challenges and echo is calling malloc, that stands out a lot. argv, and it never gets freed, not necessarily an issue, but something to note, I guess. So no one seems to free this argv. But if we think back to the previous levels, this is doing a malloc of size 32. In theory, we can control this malloc. We can abuse Tcache in a way that or maybe not control it, but at a minimum, we can do a use after free, at least based off of the pattern of the rest of these challenges. So we malloc 32 bytes. In theory, we could have another allocation with a reference to this malloc. And that is useful. The reason it's useful is if we just think back to the previous level we looked at where we did code execution, and if we see here also within IDA that we have this win function, the classic win function, it might be the case that what we need is arbitrary code execution. That maybe this challenge is going to be modeled after the previous one. If we want to, again, get a little meta game-y. But unlike the previous level, so this was back when I was on level 10, and we could see it was telling us where the stack was and where the binary was. But now when we're on level 11, it doesn't tell us that. So we learned in level 10 how to abuse the heap to get arbitrary reads and writes and use that for arbitrary code execution. And in order to do that, we needed to know where the binary was and where the stack was. And in this case, we had malloc free put scanf quit, and in this case, we have malloc free echo scanf quit. So we don't have puts, but we have something similar enough. But it's similar enough that, and different enough, that hopefully maybe a slightly natural question arises. Can we use just the fact that we move from puts to echo to recover this information? Because if we could recover this information, we could do the same solution as level 10. But we would have to somehow use echo or the implementation of echo to recover this data. If we look at IDA while we're reversing it, we said that we could probably have a use after free with this malloc, so still have a reference to it. And then, very interestingly, argv0 is being set to this string bin echo, which is going to be a string that's located somewhere in the binary. Can I double click on it? Yeah, so somewhere in the binary right here at 33fe is just the constant data bin echo. And it's using a pointer to this located in here. If we could leak out this pointer, we would now know where everything in the binary is. We just lost where we were. We were in echo. So if we could leak this pointer, we would know where everything in the binary is. That doesn't tell us where the stack is though, but if we could leak where this is, or this, either one, I think, right? So data stir got stir copied from this. So we copied this, which would also be located in the binary. For some reason, it's not letting me double click this, but it is, well, I guess it could be inlined, but this is getting copied to this thing on the stack, which is getting put here. And then this is, well, I guess we don't know for sure if this is on the stack, if allocations are on the stack. I think they are. Yeah, this is on the stack within main's stack frame. So either one would be on the stack. Go back to echo. So moral of the story is that if we could leak out this pointer, that would tell us where the binary is, and if we could leak out either of these, this would tell us where the stack is. And we have the ability to do a use after free, because this malloc is going to happen, and if we do, for instance, what's the best way to show this? Probably going to need GDB to show this. If we do, how should I show this? If we run and we do malloc 032, so the same size, and then free 0, and then we could either just do echo and see that this disappears from Tcache, or we could do we could pause real quick, break on malloc, and then continue, and then call echo 00, so allocation 0, offset 0. And we will see that we're paused in malloc now. And if we finish this function, we should see, actually, and real quick, if we do BT, we'll see we're in this echo function, and then malloc from the echo function. And then, so we had this 2C0, 2C0. If we finish malloc now, we will see that we got 2C0, right? So that just absolutely confirms it. And also we'll see, this is interesting actually. We just immediately printed stuff. This should definitely be jumping out to you whenever you see the magical question marks. This is a very good sign in exploitation. These question marks are basically just pure money. And maybe we want to investigate those more now that we're randomly seeing those. Let's do challenge and pipe it to XXD. And then let's do malloc 032, free 0, and then echo 00. Obviously, this is kind of a pain to read initially, but hopefully we can locate, yep, this data string, and then we have these non-printable characters, which is being stated with a dot in the case of XXD. And if we look for what this is, so DATA colon space and then this stuff. And then eventually a new line, which makes sense because eventually echo is going to include a new line at the end. So this seems to be the data that it's printing out. This 562F 8B 84 C3 F8 and 56 sounds like it could be the location of our binary. 56, you know, something starting with a 5, it's very binary and pi mode-y. And that probably makes sense from what we were talking about with IDA, that if we manage to echo out allocation, so in this case what we're doing is that we made allocation 0, and then we freed it, and then this malloc returned that same allocation, but the thing that we passed into echo is basically what it just mallocked. So this malloc, this echo is referencing basically the thing that we just mallocked. And we're setting now the first 8 bytes of that to be somewhere in the binary. And then the next 8 bytes to be somewhere on the stack, and then the following 8 bytes to be somewhere in the stack, and then zeros. So this bin echo, we can see ends with a 33F8. So definitely with pi accounted for, it should end with a 3F8. So if we go back 3F8s, we're going to see that. So we have this 3, F8. And then obviously the rest is influenced by pi. So there's our 3F8, and that follows exactly from this string bin echo. So we just leaked out the address of bin echo. So now we know where everything in the binary is. Hopefully you can see that you could do a similar thing for the stack. So there's a question, what does that data signify? Could you be slightly more specific? What do you mean? So this data is a pointer to this string right here. So when the program gets compiled, right, at some point we had source code, G echo. At some point there was source code for this program that basically said, hey, set argv0 to this string literal bin echo. And when the compiler went through and produced this binary, it put this raw data somewhere in the elf. And what it's doing here is it's saying that this is equal to the pointer that points at this data, this raw data. And where this raw data is located is at offset 33F8 into the elf. And we can see that when we're getting this leak, that the thing that we're leaking out is this 3F8. So that is what that data signifies. It's the pointer in the elf to that string. In fact, I guess we could show it. How would I show this with GDB? Okay, here's what I can do. If I copy the challenge, just to quickly get rid of the suid bit, and then we do GDB baby heap level 11, and we run, and what we do is, how do I do this? No, this is not what I wanted to do. If we just run it with XXD, baby heap level 11, pipe that to XXD again. We do malloc 032, free 0, echo 00. We get our data again. And again, this contains a 3F8. But now if we switch over to another terminal and we do ps-aux grep for heap, so we have this challenge running. And the reason I got rid of the suid bit is so that I can now GDB attach to this process. So if I do GDB, we'll specify this and then attach. Oh, this is unfortunate. I need to go into practice mode, I think. Because it's not a child. Yeah, let's just switch to practice mode to show this. Okay, so if we do this, oops, we wanted to pipe that to XXD, and this time we can just run it suid, who cares? And we do malloc 032, free 0, echo 00. Okay, so we have this data coming out that has our 3F8. And if we grep for heap and sudo gdb challenge blah blah blah, and then attach 103. Okay, and what we're going to try to do is convert this back into its pointer. So we have this data right here. And maybe we'll just quickly open, let's SSH real quick. Open IPython. And let's convert this into our address. So if we copy this, is there a good way to do this? Nah, let's just do it by hand. Okay, 0x, so F55, D6, 68, 6D, A3, F8. Okay, this is the pointer that we leaked. Obviously, if we use pwn tools to ingest this, we could use like pwn U64. The issue is that we're using XXD, which is printing it in these like 2-byte chunks that have endianness like all over the place because of that. But we manually did this. And then if we do x/s at that address, you will see, as we said, that that is a pointer pointing to this string. So that is what we just leaked. All right, are there any more questions on this level? Hopefully you solve 10 and then you come to 11 and you use this sort of principle. You'll see that 11 can be solved. Not seeing any more questions on this level. Were there more questions in general about this module? Okay, there was right at the start, someone was interested in 12. Oh, yep, I guess you're asking again. Okay, we're doing 12 still. Sure, let's take a look at 12. Okay, 12, start. Okay, what does this challenge give us? 16 allocations, heap stuff. Okay, this challenge looks very different because of the functions we have access to. So we have malloc free, put scanf, and then we have these new crazy looking functions. Stack free, stack scanf, stack malloc win. Okay. So this function sounds super cool. Anyone that's talking about winning is always great. So let's just call that stack malloc win. I want to win. Okay, we don't get to instantly win, which makes sense because it's not called win, it's called stack malloc win. And this tells us the rough logic of it. And it's basically telling us that if malloc of 89, so it's going to probably call malloc 89, and if it is equal to this address, we get to win. Okay, so we need to force a next malloc of 89 to equal this address somehow. Okay. And also telling us malloc usable size of malloc of 89 is equal to 104. So some sort of rounding mechanism of this malloc 89 goes to 104. And then probably what it's telling us now is that it did malloc of 89 and it got this address, and therefore we did not win. Very sad. Okay. We have these other cool looking functions. So we have special stack free and stack scanf, which sounds nice. So if we do, let's see what stack free does. Not cool. But what did it do? So it attempted to free this same address. So it's attempting to free the address that we can win on, and it just failed. It did not like it. And if we look, maybe we care, maybe we don't care. I'm kind of interested right now. Let's see, what does this double free or corruption really mean? We look into the malloc source code. Maybe we can quickly understand why this message ever pops up. double free or corruption out. This appears once. Okay, so this is where this is happening. What function are we in? We are probably in free. We are in fact in free. Where in free are we? So the immediate thing that it's checking, something contiguous, not really sure what that's going to be all about, but okay. And next chunk, so some sort of next thing is not null, maybe? Oh, no. And next chunk is greater than this top thing. So whatever that means. Oh, the top thing plus chunk size of this. And then there's comma 0. Where is this comma 0 with? Am I misreading parentheses? Is this valid C? You just do comma 0? This is like a Python tuple, isn't it? What is this? Oh, no, this is an argument to expect, isn't it? I think. Okay. Hold on. Parentheses. So we've got one open. And it's closed. Okay. Yeah. This is all the first argument. This is the second argument. Okay, that makes more sense, I think. Okay, so this, as someone that's read libc source around malloc a few times, I have no idea what this is on about. I mean, I have some clue, but it's not immediately obvious what this means other than it's checking to see a way in which data can be corrupted. But I'm not totally sure what AV is. I think AV gets passed. Something sort of malloc state. It's checking if this malloc state thing is contiguous, which we'd have to look to see what that means. And that if the next chunk is greater than kind of the top of malloc plus the chunk size of the top of malloc, that it's not happening, it's going to crash out. Okay. I'm going to say that it's not super clear why we're failing immediately. I would probably at this point not take the route of trying to really understand the source code of malloc immediately, and instead look at kind of our understanding of malloc chunks instead. So what do I mean by that? So if we do, what do I want? Let's do Emacs. I want pwn.debug back because I want to do, I want to look at memory with pwn.debug. So if I do source opt pwn.debug gdb init.py, do we need this? Maybe we will. Okay. And if we run the challenge now with gdb, we'll see what's maybe going on. So if we run it, and if we do stack free again real quick, we can see, yeah, we're catching that abortion or whatever that when it's failing. Okay. We saw that message, and actually maybe we can have some idea using the source code of what's going on. If we look into this int free, we see, okay, this is where we're going to call malloc print error. Oh no, this would be the next. It's not super easy to look back instructions, but we can just guess offsets. -20, why not? Okay, so this is what was actually being called. Malloc print error. No. We did this. Let's just break here. Why not? Let's go crazy. Trust as a way of trying to understand what's going on. Oh, another one. They're crazy. Are they at least following us? Are we at least gaining followers from these spammers? Maybe I should turn follower mode on. Then we at least gain followers. It'd be cool. Become famous. We'll make them be the ones that follow us. We won't even have to buy followers. Okay, so if we break here, which seems to be, if I had to guess, it's going to be related to this. Do I really want to go down this route? No, I don't want to go down this route. This sounds too annoying. This is more of like a, this sounds like a last option of really going through and understanding this. Hopefully we can figure out what's going on without going down this route. Okay. But as a last resort, this would be the route I would go down. Really understanding how this condition is failing, basically. And then maybe we would see memory being dereferenced to determine this condition related to this, and we'd see what it's talking about. And it's possible we could go that route, but sounds like a very annoying route. Okay, instead, let's do this. Let's do malloc 032. You know what I should do next time I stream? I should probably put the camera in the top right, because I keep getting so close. Oh well, next time. Malloc 032. 30. Okay, so now we have Tcache being used. And if we do stack malloc win, just to kind of get the address that it's interested in, and you'll see why here in a second. If we now look at this, so if we break out by hitting Control C and then basically pausing in this read syscall, and if we, okay, so if we do like Tcache bins, see that this is the 12C0 that this was talking about that we freed. And if we do viz heap chunks, this thing right here, this is what this chunk actually looks like in memory. So we have the key, which is right here. We have the next pointer, which is currently null. And then we have the size of this chunk. And then we have the previous size of the chunk, basically. Right? If we look here, size hex 31, prev size 0. Yeah. And I'm not entirely sure why, but it puts the prev size kind of in like the previous colored chunk. I think that's because of the way that it's actually implemented, that it puts the metadata at the end or something. I'm not sure. But this is the prev size, this is the size, this is the next, and this is the key. And so basically these 4 things, these 32 bytes, are all of the metadata of this chunk that when we are able to go and call, what was I going to say? If we go and call malloc, stuff can happen. But really what we're interested in is what allows us to be able to free something. So instead, for that, what we'd want to do is let's continue. Let's malloc this chunk back again. So currently we have this chunk freed. Let's malloc it and see what it looks like. So if we do malloc 032, so we got this C0 address back, and let's pause again, and let's do viz heap chunks. Okay, so this is what we're looking at right here again. And again, these 32 bytes are a malloc chunk. And obviously this data here could in theory, be anything right now because we're malloc and we will return this address. We asked for 32 bytes. It's fully within our control to change this data right here. But this right here is some sort of metadata that the heap is using, as is this right here. So these two things, if corrupted, could probably be not great. So for instance, let's just as a test, take this address. Let's see what happens if we modify this right here and make this be like 8As. And we can do this with GDB to quickly see what happens. So if we do, oh, how do I want to do this? Can I do call read 0 this 8? I want to go 8 bytes in to get there. Will this work? Is this valid GDB? Call read 0. Let's see. Nope. I make parentheses around it. Make it look like a C function call. Oh. 1, 2, 3, 4, 5, 6, 7, 8. Let's just set that to 8As. Okay. Viz heap chunks. Don't know what just happened there. What just happened? Oh, probably this is super unhappy now. Because we just messed with heap metadata, and this cool pwn.debug tool that's using heap metadata to figure out how to show us the heap probably isn't the most excited. Very sad. How do I get that address back? I don't remember what the address was. This. Okay, whatever. We'll just look at it ourselves without using this cool visualization stuff. 8GX. Okay. Wait, what? What did I do? How did this not become 8As? What is this? Wait, this looks like ASCII though. Okay, probably doesn't matter. But I'm curious. Okay, that's what happened. For some reason, our 8As didn't end up there. Instead, us attempting to type out this command ended up there, which is strange. But we'll roll with it. Either way, we corrupted it. And now, so this is allocation 0. So now what happens if we free this? So this is now the metadata for this chunk. If we do free 0, continue, and free 0, we are failing. And how are we failing? Is it going to be an RDI that our message is? RSI? Where did this message go? Oh, right here. Okay, we failed in a different way. When we went to free this, we got this message. So we can see metadata. Metadata matters, right? It matters. We did something else that caused us to fail. M unmapped chunk invalid pointer. M unmapped chunk. What was it? Oh. Invalid pointer. So we failed in this way. It thinks it's mmap. Yeah, probably we used one of those bits that implies that the allocation was m-mapped. And this 7 would be, or no, it'd be 0. No. Why am I so confused right now? I think it'd be the 6, right? Yeah, the 6, which if we do instance, just to quickly see, bin 6, these would be the 3 bits being used. And what is it? The second one says that if it's a 1, it's m-mapped. Is m-mapped. Yeah. this second bit. So it thinks it's M mapped because of this being here. And however it just went through and freed it, basically the logic it went through, it failed, and it aborted in that way. This is a long way of showing that if you corrupt the metadata and then you go and free something, libc is not going to be happy. And what's going on here when we do this stack free is that effectively the metadata is already corrupted because it's just arbitrary memory on the stack. So we rerun the program and we do stack malloc win, and I guess you can't quite see stack malloc win, and we see that this is our address that we're looking for. And if we do x8gx, or wait, we need to pause real quick, x8gx of this, but we want to go back 16 to start at looking at our metadata. Really, back 8 is the first bit of metadata we're looking at, but we saw that those bytes could be 0 because they were 0 for successful freeze at least. 80, let's look here. Okay, so this is how we're looking at that chunk that we want to. So we saw before that when we do stack free that it's using the same address here. So when it's going to free this, it's looking at this metadata here. This metadata right here. So this isn't a 0, and we've seen it only so far successfully free something when this was a 0. So we might need to figure out how to make this become a 0. But this is definitely bad. This is like, who knows what this is. This is not good metadata. Very, very not good looking metadata. But what if we could make this be good looking metadata? Do we still have this in our history? Not exactly. Okay, so if the problem here is that this is bad metadata, what would be good metadata? And a quick way that we could test that, here, let's just run it in another terminal without GDB. That if we do stack malloc win, and this is doing malloc 89. So now if we want to replicate this sort of size of malloc 89, whoops, that is not what we wanted. Malloc 89, or malloc 089. So we just malloc for 89. And what would it look like for this to be valid enough for us to free it now? Because right now we know that if we call free on allocation 0, it's going to succeed. But for some reason, like stack free is not succeeding. It's aborting, and it's related to the metadata. So I'm not looking at, how do I get to look at the metadata? Okay, let's do this from GDB. Continue. Malloc 089. Okay. So we got this back as our allocation. And if we want to look at the metadata now, we look here, we go back 16. Okay, so this is starting with 0 and then having all of this to 71 indicated to libc that this was a malloc chunk that worked for size 89. The reason for that is this 71, if we do heap, so we can see here the 30, but it's going to be 20 because this is where the metadata starts. So 20, which is kind of what we printed. It says it's size 71 or hex 71. And if we do tcache bins, tcache, what am I, oh, that would be empty, of course. But 71, I guess here we can show it. If we do free 0, it's for this size range. If we do Python 0x71, you'll see obviously that this hex 71 is greater than this range. And the reason for that is that the size is including the size of the metadata, and then obviously it also has this bit being set. So if we make this hex 70 instead, obviously to remove those 3 last bits, oops, that is 112. But if we just subtract another 16, now we're within the range. Is it 16 or just 8 actually? Yeah, it's just 8 to declare what the maximum size is, I guess. So even though it's hex 71 and it's up to 104, the size is close. It's just slightly different because it's being computed in a different way. It's including like metadata sizes, I think. Okay, either way, doesn't matter because we alloced something 489 and we saw that what needs to be here is hex 71. So if we can do the following, and we're going to cheat using GDB, but we saw that we have like stack scanf, so you don't have to cheat. And we want 71. So if we want to put 71 there, fortunately this is an ASCII character, so we can just roll with it. It's going to be a Q, which is very cool. And we do stack malloc win. What was that looking for? This address. Okay. And x8gx this with 80. Okay. So we want to set this all to null. And we want to set this to that hex 71. Okay, what's the easiest way for me to do this? Wish I remembered the syntax for set. To go back through embryo GDB and see what the syntax is for setting memory. Something like, I think you can specify the type. So if we want to say that this is a uint64t pointer, is this gonna work? It zeroed it out, so yeah, I guess so. And then this we want to say is hex 71. So we didn't even care that it's ASCII for the purposes of this. Okay, so we just manually using GDB changed this metadata. And now if we go through and we call stack free, we're going to see that it did not fail this time because we have successfully modified this metadata. And we'll even see that this location now at 90 is sitting in Tcache. We're ready to go. We call stack malloc win. We're going to see that we succeeded. It's failing because we're in GDB and we don't have permission to read the flag. But using GDB, we could see how we could modify the metadata to accomplish this. But fortunately, we have this stack scanf function. Whoops, that was not correct. Either way, we can run it again. Stack scanf, we can see that we're scanfing to here. Hold on. If we go stack malloc win, it's looking at this address. If we do stack scanf, it's looking at this address, and this address is before this address, and it's giving us up to 127 bytes, db0, but this is less than 127 away. We'd have to use pwn tools to get a bunch of null bytes in there, but this approach would work. Hopefully it makes sense that basically this challenge is all about understanding the metadata, and we're kind of going, I don't remember the exact, is it House of Spirit maybe? I don't know. It's one of those House of somethings, and basically we're forging our own chunk here in this level. House of Spirit, yeah, it sounds like a very spirit-like thing, you know, kind of putting life into creating a new chunk. It's very, very cool. You zeroed everything, but what was that hex 71 representing? So that was representing the size. So if we do malloc 032 and then free 0, right, we have a size thing in the metadata. So that is what, in the case of, I mean, obviously it was 71 instead of 31, but it was the size metadata. And then this is obviously the zeros. Yeah. So these are the 2 bits of metadata that matter. I'm not actually 100% sure. You can go and test this yourself, I guess, if you're interested. Maybe this doesn't matter. I don't know. Maybe this could be a bunch of A's. Easiest way to figure that out would be to test it. Alternatively, of course, you could read through the source code. That sounds miserable. I would probably, if you're interested in knowing if this metadata matters, just change it yourself, see what happens. But yeah, definitely we can see just looking at this that it would work if it was 0 and then some size. Okay, so there is another question. Can you please give a pointer for 15 on how to allocate a stack address using read? Pointer for 15, how to allocate a stack address using read. So read won't do an allocation. Allocate a stack address. Like read will never call malloc, for instance. Trying to remember what 15 is. I guess we can very quickly look at it. I won't go through the solution, but we can at least give a pointer on it. Okay, 16 allocations, malloc free, echo read quit. That's it. And there's probably a win function in here. Ref win, there is a win function. So yeah, something to note is that instead of scanf, we have this read function, which has a slightly different implementation than the scanf implementation. What to give as a hint? So in previous levels, you've used scanf and you've kind of abused the tcache linked list by doing a use after free. I guess the other thing to point out in this challenge is that if we do malloc 032 and then we do free 0, we are going to see that something magical just happened. We finally added a little bit of security. Hopefully it's been standing out to you that the clearest security mechanism that could be added to all of these challenges and implemented by the person writing this program would be to just null out all of these allocations after we free them. This is going to make use after free like no longer possible because we've nulled it out. And if you start scanfing to it, now you're scanfing to a null address. This level finally does that. But even still, the game is still on. So the thing to think about is that in this case we have read instead of scanf. And this read is not doing bounds checking. It allows you to go past the end of your allocation. And there's going to be all sorts of heap chunks past that allocation, all sorts of metadata. So think about how getting an out of bounds, basically being able to overwrite data past your chunk, even in the case of use after freeze no longer immediately working, think about how an out of bounds read will still allow you to accomplish your goals of winning. Directly to answer your question, there's no way to make read allocate a stack address. Well, read won't call malloc, for instance. Of course, you can do metadata tricks to get read to allocate you a stack address in terms of messing with Tcache. Of course, you don't know where the stack is yet, so you'd also need to do some things that'll let you know where the stack is. Of course, we have this very cool looking echo function that we talked about before. All right, I think that is all for this office hours then. Hopefully everyone will be able to finish everything before 4 p.m. tomorrow, because that is when it is due. We will not be able to extend the modules anymore because we're out of extension dates, unfortunately, in order to get through all the content. But you know, there's extra credit, there's more modules, there's late credit, etc., etc., etc. Okay, all right. Thank you everyone for joining, and as always, feel free to ask more questions in the Discord. All right, see ya.